So next we have Ken Roy. Ken, are you here? Hey, there you are. Hey. He's going to talk to us about the problem of low gravity and human physiology, and he has a potential solution for us. I can't wait to hear about it.
I'm going to be talking about, really a question of gravity, an area that we just don't know much about, and potential implications for trying to establish a human settlement on, small planets and moons. Earth life has evolved, as far as we know, has evolved here on Earth in a 1G environment. And Earth life, it's got to learn to deal with that gravity. It's probably capitalized on that gravity to some extent. So, we're reasonably healthy, again, because of the gravitational field we're in, maybe despite because of the gravitational field we're in. We have some experience with the International Space Station where astronauts spend, 6 months and sometimes longer in essentially zero-G conditions. And the outcome hasn't been real positive. Exposure to zero-G for even a few months seems to cause pretty significant changes in the body. And one researcher pointed out that a lot of these changes seem to mimic accelerated aging. So we have those 2 points. I guess the key question is what level of gravity is necessary for human beings to be healthy in the long term? And does that have to be constant, or can you have Earth normal gravity for, say 12 hours and then run around on the surface of the moon for another 12 hours and then come back? Does that allow you to be healthy? We just don't know. We just don't know. Microgravity, again, from the International Space Station, if you spend time up there, the body decides that the bones don't need to be as strong as they are, so the calcium is reabsorbed. Sometimes that leads to kidney stones. Muscle loss is pretty well demonstrated. I think the previous speaker talked about that. There was a recent study where they looked at calf muscle strength, and after 6 months on the ISS, it was reduced by 32%, and this is with exercise. Inter-ear problems, do occur. Sometimes they're not reversible. Visual problems sometimes occur. Some reading I was doing said male astronauts seem to be more susceptible to this than female astronauts. The spine lengthens, immune system doesn't seem to work as well. Sense of taste is not as good, and drugs seem to act differently. So there's a lot of things that happen in microgravity that aren't real positive. And again, as one researcher said, it looks like you accelerate the aging process. So it comes down to the question that right now we have 2 data points. Here, health is reasonably good if you have a 1G gravity to live and work in. And then we have microgravity from the International Space Station. And fundamentally, the long-term health prospects of people living in zero-G is not good. What we don't know is how you connect these 2 points. We essentially have no experience in this region. We had some astronauts on the moon for a little bit, but probably not long enough to be able to draw any conclusions. So is this one way to connect the points? Yeah, but is this the way it works? Or do you run into a situation where a little bit of gravity gives you a lot of health benefit? Or do you have to have essentially almost normal Earth-like gravity in order to be healthy? We don't know. Or is it more complex? Here, maybe children need gravity, but once you become an adult, perhaps you don't need as much gravity, and once you get older, gravity might actually become a problem. So, afraid so. So the question of gravity, we need experience, we need to understand what we're dealing with before we begin to venture out into the solar system and establish, settlements and bases. It may not be a problem, maybe a little bit of gravity is all you need. On the other hand, maybe not. And when you get to the question of children and pregnancy, we're really in the unknown area because for some reason, the ISS won't let us bring children and pregnant women up. But we do know, or we're fairly confident, that growing children do need gravity in order to grow bone and muscle, in order to develop balance abilities, in order to learn how to walk and run. If they don't have the adequate levels of gravity, we don't know what the consequences are, but it's probably not good. And pregnancy is pretty much a complete unknown. So why does this matter? Because as we venture into the solar system, there's a lot of worlds, rocky worlds and worlds of rock and ice that look like they would be very useful. First of all, they're fairly common. They have a lot of resources that would be very valuable. They have a small gravity well, which means you can get there and get off pretty easy. We have one really close to Earth, so we can practice on it. And they're just useful locations to establish bases and perhaps human settlements. But all of them have a low gravitational field, and so that gets back to the earlier question, when is gravity high enough to allow for healthy humans? There are a number of people that have come up with interesting designs for lunar settlements and Mars settlements, and here's one. And some of them are pretty nice. Looks like it could be a very pleasant place to live. But again, you've got the gravity question to think about. The only way to supplement gravity is with artificial gravity, and the only way we know to create artificial gravity is with centripetal acceleration. The space settlement people have assumed that 1 RPM is about the maximum that we want to get into. This is an assumption, maybe an educated guess would be a better term. And for our purposes, let's just assume that the worst case condition is true, that humans need Earth normal gravity in order to function. You may want to provide Earth normal gravity anyway so that they can come and go and return to Earth. So can we do that? Well, okay, here's one possible solution. Whenever you're on a moon or a small planet, it does provide you with a little bit of gravity, and we know how to calculate that. Centripetal acceleration, again, we know how to calculate that. It's going to be perpendicular to the gravitational acceleration vector, but we know how to add vectors. That's pretty simple. This would be the combined total acceleration that you're going to experience. And if we assume that that has to be Earth normal, then it's 9.8. So we know what gravity the moon or the planet provides. We know what gravity we want. And we can calculate this. And we can also calculate this angle here, which tells you how far off the vertical you have to tilt the floor in order to make the floor seem level. So, just fairly basic math. Now, the PowerPoint police would probably arrest me for this slide. It's just too busy. But here I have, assume you want various gravities. Here's one gravity. Here's the RPM of the rotating structure. Or you can have an object running around in a circle, same thing. And it seems like the sweet spot seems to be about 1 RPM and 1 gravity. In this case, I'm looking at Mars and Mercury. Mars and Mercury, strangely enough, have essentially the same surface gravity. So this chart really applies to both. And this number here is the radius in meters of a rotating structure or the rail system that your object is going to be running around on. And of course, this is the angle of the floor off vertical so that the floor seems level. And we can calculate that for the moon. Again, here, 1 gravity, 1 RPM, and the radius needs to be 880 meters. And the floor needs to be tilted, from vertical about, 9-10 degrees. And Pluto has a very small gravitational field. This is pretty close to what you would find in orbit. So 1 gravity, 1 RPM, you're up to 890 meters for the radius. So the answer could be Lunar Mag Lev System. We've had someone already talk about magnetic levitation trains, and it turns out that 1 gravity, 1 RPM on the moon, you need 880 meters, and in order to translate that into movement, you're going 332 kilometers per hour. If you're willing to accept 0.9 gravity and 1.5 RPM, you reduce the radius to 350 meters, and then you're only going about 200 kilometers per hour. But again, the Maglev systems that the Japanese are using, they have one train that goes up 600 kilometers per hour. So the Maglev technology that we're looking at is certainly well within our current capabilities. Maglev is very efficient. You can extract the energy that you put into it when you slow it down. And you can use it to provide Earth normal gravity for long periods of time. And of course you can stop and let people on and off as needed. Magnetic levitation, there's different ways to do it, but the trick is that the vehicle is sitting on a magnetic field. Magnetic field is strong enough to actually levitate it. And one big advantage of magnetic fields is they don't seem to wear out. And if you want to move the thing, again, you play with magnetic fields, you push-pull magnetic fields on the train or the car, and you can accelerate it up to high speeds. And you can also decelerate it and extract energy from it. So this is one graphic showing one way to achieve Earth normal gravity on the moon. And this would be your Maglev rail system. These are your Maglev cars. This gives you some idea of the 9-degree tilt that you have to get in order to have the floor seem level. So if this crater is has a radius of 880 meters, then you're good to go. Or it could be bigger. Just understand that the bigger you go, the slower the RPM, the faster your train has got to move. And here's another view of it. Train moving along the side of the crater. Another view of it. And here's a picture of a Maglev train, Japanese Maglev train. In 2015, it set the speed record of 600 kilometers per hour. So again, we're looking at technology that pretty well established. Now this is highly streamlined, again, because it's got to deal with atmosphere. On the moon, that may not be a constraint. Okay, this is a train car that a lot of people think of when you say train cars. But for our lunar train, this may be more what you're dealing with. It could be a fairly comfortable place to live and work, but it's not really a place to create a long-term settlement. You wouldn't want to raise children in this kind of environment. Now, if we go to the Stanford Torus, suddenly we're looking at a space settlement that is pretty comfortable. This was a 1975 design. There have been others since, but use this as kind of a benchmark for our purposes. It was designed to hold 10,000 people, 1 RPM, 900 meter radius. It was designed to provide 0.9 to 1 Earth gravity. The tube itself is 130 meters in diameter. It weighed 10 million tons, and it had shielding 1.7 meter thick. And I think there are people trying to improve this design now, but as far as a benchmark for us, it's an interesting way to go. Here's a sectional view of the tube section. Again, it's 130 meters, and then this would be the floor. The center of the torus is back here, about 880, well, let's see, this is in orbit, so about 895 meters. Now, for our purposes, let's just take it to the surface of the moon and drop it there. We're going to support it with a Maglev system. Here's the lunar surface. And again, here's this floor tilt that we were talking about earlier, about 9.5 degrees. So if you're standing here, the floor will seem normal. And again, we're able to reduce the radius a little bit. You run it up 1 RPM, and you can, again, experience Earth normal gravity on the moon. And you can have a train, that speeds up to the speed of the Torus, let people on and off, and then it slows down, and you can, have access to the surface of the moon. Okay, again, let's go one step further. Dig a circular crater or cavern on the moon, and then we drop our Stanford Torus in there. Again, we have our Maglev system, and then we roof it over and put lunar surface on top of that, and then all of a sudden we don't have to worry about radiation shielding for the Torus, because your lunar surface is going to provide all the radiation shielding you need, and it can be substantially more than 1.7 meters. So we've improved our radiation shielding quite a bit, but we're still living in this case, the Stanford Torus for all effects and intentions. Pretty nice. And if you pressurize this cavern, then the Torus itself doesn't have to be a pressure vessel, and you've simplified the design constraints for your settlement by quite a bit. With a Lunar Tori system, the industrial and agricultural areas don't actually have to be on the Torus. They can be in the normal gravitational field that the moon or the planet provides. But we can also address the need for, or the assumed need for human gravity. This is, again, an open question. Do we need Earth normal gravity for this kind of settlement? And, we need to run the experiments before we can answer that, but let's assume it does. At least we have a way to establish a human settlement on the moon, on Mars, on Mercury, on the moons of the gas giants. And as a final point, two such tori on opposite sides of the moon can provide pretty good insurance against gamma ray bursts wiping out the human race. With enough shielding, one would probably do, but if it's close enough, you want a planet between you and it. So, ensuring survival of the human race is not a bad thing. So yes, we can establish, human settlements on, moons and planets, small planets. Even if, our physiology requires that we, live in a 1G environment. And I think that's, that's an option. But we need to run the experiment to find out where, what our gravity limitations are. So at that, I guess I'll leave it.